Thank you. Thank you very much for the introduction. So today I will speak about Fourier interpolation. And so let me start with the main definitions. So let's consider some space of functions, for example, in Rd. And for this talk, mostly D will be 1, even though other dimensions also will be considered. And so let V be a space of functions, and if we want these functions, this space to be somehow big enough in order to be interesting. For example, this could be the space of Schwartz functions, or the space of Sobolev functions, or some other spaces we will speak about later. And so what is important for us is that on this space, we are able to compute the Fourier transform. And so we define Fourier transform in this way. So here, okay, so here there is a small typo. Of course, this should be, we should integrate with respect to the variable x. So this is the, after we have defined the Fourier transform, we can consider the following question. So suppose that we have a pair of subsets in our space Rd, and suppose that we know the values of function f everywhere on this set lambda, and we know the values of its Fourier transform everywhere on the set lambda tilde. So the question is, then do we know the function f itself? Or another way we can say, if we know that function f vanishes on lambda and its Fourier transform vanishes of lambda tilde, is it true that our space X also should vanish everywhere on Rd? And so here's one classical example of such a Fourier uniqueness pair is the set where we take set lambda to be the set of all integer points. And then this, the lambda tilde will be the set of real numbers with interval minus 1/2 removed. And so we know that, so this is a classical Shannon-Whittaker interpolation formula, and different variations of this formula. They tell us that if our function is a class which is somehow nice enough, and then if its function vanishes on all integers, and its Fourier transform vanishes on outside of the interval minus 1/2, then the function has to be 0. And so we have not only this uniqueness result, but we also have a recipe of how to reconstruct our function f. So suppose that we have function f such that its Fourier transform is supported on this interval. So here we can also, we don't have to work always with interval minus 1/2. We can also rescale. And so instead of pair z r minus 1/2, we can also consider pairs 1 over w times z and r minus this interval minus w over 2. And so we know that if our function has Fourier support on this interval, and namely if it belongs to this Pauli-Wiener space, then if we know the values of function f at all integers divided by w, then we can reconstruct our function f back. And so it will be, and the role of interpolating basis here is played by the cardinal sign functions. And so we can make a more, inspired by this situation, we can make a more general definition. So suppose that we have now two spaces, V and W, and they will be two different spaces of functions, possibly different. And we would say that lambda and lambda tilde, it is a Fourier interpolation pair if we can find two sets of functions, one set of functions. Sorry? Is there a question?
No, I think someone just did not mute himself.
Okay, so the first set of functions is labeled by elements of our first set in the pair, or is labeled by elements of set lambda. And the second set of functions, it's labeled by elements of lambda tilde. And we assume that these are functions in our second space of functions W. And so we say that our pair, it's a Fourier interpolation pair if we can reconstruct function f from knowing its values at this, the values of functions at the set lambda, and knowing the values of its Fourier transform at the set lambda tilde. And we use these functions a and, sorry, here again, a small typo. This might be different functions, a tilde. And so we're using functions a and a tilde as an interpolating basis. And actually, so here I've written this Whittaker-Shannon formula somehow in this simpler form. When we know that function is in a polylinear space, then we only need this many functions for the reconstruction. But there is actually a more general variant of this formula, which works for wider class of functions, because here we can also add integral over this interval minus one, integral of minus w over 2 to the w over 2. And here would be Fourier transform of y, and here will be some measure. So of course, also this sum, if our, in the case our sets are not discrete, we can consider these sums also more generally. They might be actually some kind of integrals.
Maryna, there's some questions in the chat session.
Yes.
I think there might be some, the questions are concerning where AL lives. AL lives in V, is that correct?
Yeah, but actually, but this can happen that these functions, they live in W, but after we are summing up everything, then this function will live in V back. So, okay, so here for, and we will have examples like this for, because it can, how it can happen, it can happen that this information we are collecting about function f, it is somehow a redundant information. And so this will be actually about my next slide about free interpolation, because interpolation is not always free interpolation. Okay, so next slide is actually about free interpolation. So now suppose that we have also fixed some spaces of functions on sets lambda and lambda tilde. And we would say that this pair of sets lambda and lambda tilde is a free Fourier interpolation pair if this map, which takes a function f from space V and maps it to a product of these two spaces V of lambda and V of lambda tilde, is an isomorphism. And if this map, which we have constructed in the previous slide, it is an inverse of this map. So namely, it means that we can not only reconstruct functions from its values on lambda and lambda tilde, but we can assign to f any values on lambda and lambda tilde we want, and we will always finding a function which matches those values. And actually, in this case, if this works, then it's not difficult to see that in this case, this space W, it has to be equal to the space V. Or at least that we can find, we should be able to find, it should be logical to search for our interpolating basis inside of space V itself. And so here is the list of some. So I've recalled the classical results on Fourier interpolation. And here's the list of some more recent results on this topic. And so maybe like one big difference from the classical Shannon interpolating formula is that in all these cases, both sets lambda and lambda tilde, they are both discrete. As in the classical case, lambda was discrete, even though rather sparse, and lambda tilde, it was an infinite and an uncountable set, which had like huge, actually infinite measure. But it turns out that this Fourier uniqueness and Fourier interpolation, they can even work for both for discrete, for sets lambda and lambda tilde both discrete, even though the price for this is that both sets, of course, they have to be much denser than the set of integers. And so the first result I want to talk about, it's the formula we proven together with Danilo Radchenko. So we have shown that we have a Fourier uniqueness interpolation and even free Fourier interpolation for this pair of sets, where both lambda and lambda tilde, they are the sets of square, so roots of even integers taken with plus and minus sign. And so this is maybe not very accurate statement here. So all this is true up to finite, up to corrections of finite codimension. And then there was a very interesting result of Andrei Bondarenko, Danilo Radchenko, and Christian Seip. And they proven that Fourier interpolation works for zeros of zeta function and L functions. So in particular, in the case of zeta functions, they consider the following pair of sets. So first set, they are the logarithms of integer numbers. And the second set are the imaginary parts of this non-trivial zeros of the corresponding of the zeta function or of the corresponding L function. And what they show that interpolation also is possible in this case for a specific subspace of for functions which they describe in their paper. And so these both constructions, the one which I will speak more about today, and this beautiful paper of Bondarenko, Radchenko, and Seip, they are both rather algebraic constructions. So these constructions, they work because the set lambda and lambda tilde, they have very rigid arithmetic structure. And this structure is heavily used to obtain the Fourier interpolation formula. And somehow the reward for this is that this formula can be obtained very explicitly in a rather nice form, which allows also to get a lot of extra information about interpolating functions. But of course, the price is that the construction is rigid. And just from the method itself, it's not even clear how can we move nodes, so elements of set lambda or elements of set lambda tilde even a little bit. And so there was also a series of papers with, so to say, analytic flavor, where similar results are proven by analytic methods. So first result which appears was the result of Ramos and Sousa. And they prove Fourier uniqueness for powers of integers. In our result, we have integers to the power 1/2, and they study what happens if we take other powers alpha and beta. And so what they show, somehow they consider cases if alpha and beta are, for example, much smaller than 1, or if alpha and beta are much bigger than 1. And they show that in this case, there will be corresponding uniqueness or non-uniqueness results. Also, another paper by the same authors, I should mention, attacks this problem for another angle. So here what they try to do, they try to take this arithmetic sequence, the numbers n to the power 1/2. But now what they do, they try to perturb each of the nodes a little bit. So to each of nodes of this lattice, they add a number en. However, what they could achieve, they could make this, so this en, it has to decay rather fast. It has to decay faster than, or at least as fast as n to the power -5/4. And in this case, they show that if perturbations are this small, then the interpolation formula still exists. And so they do this by perturbative methods. And finally, there was a very interesting result announced by Sodin, Kulikov, and Nazarov. And to my knowledge, this paper has not been published yet, even though there is a talk on YouTube by Mikhail Sodin, and I used this talk to quote results here. So it's from I think it's on 1st December 2020. So if you're interested in more details, then I think you can easily find it. And they introduced the notion of what is a supercritical and subcritical density of for the pair of sets lambda and lambda tilde. And this notion is rather general. And also what they can show that if this density is supercritical, then we would have uniqueness under interpolation. And if the density is subcritical, then there will be no uniqueness. And maybe finally, I would like to mention the recent interesting result of Nasser Talibizadeh, and he analyzes Fourier interpolation for the pair, which is a spectrum of the A2 lattice. And he shows that there is no uniqueness in this case, and not only in the sense of our definition, but also if we know, for example, higher derivatives of f at these points, then somehow finitely many higher order derivatives will not be enough to reconstruct function from this data. And at least it's true because the reason for this is that this pair, it's less dense than our, so to say, critical case, because not all square roots of integers are represented by the lenses of vectors in A2 lattice. And so we don't have uniqueness in this case. And so as I promised, here is a definition of a supercritical and subcritical pairs as given by Sodin, Kulikov, and Nazarov. So we are fixing two positive numbers P and Q. And we assume that P plus 1 minus P plus 1 minus Q equals to 1. And so then we consider this pair of two discrete sets. So first discrete set will consist of elements lambda j, and second will consist of elements lambda j tilde. And I think we can also assume that these elements, they are ordered, so that lambda j plus 1, it will be bigger than lambda j. Then we would say that this pair, it has supercritical density if such a limit supremum is smaller than 1/2. And so in a sense, it means that the points are denser than in our critical sequence, or one of the critical sequences, lambda n is square root of n. And they say that this pair of sets has subcritical density if the following lower limit is bigger than 1/2, and it means that the density of the sets is too small. And so the theorem, which is announced in a talk by Mikhail Sodin, is that the supercritical density, it will imply uniqueness and interpolation, and that subcritical density will imply non-uniqueness. And so this is the general picture with Fourier interpolation from discrete sets, at least how we know it right now. And so now I would like to speak a bit more about our result with Danilo from 2017. So I would like to explain the result itself with maybe adding more details to it, and then also explain ideas of the proof and the constructions of the construction of the interpolating basis. And so this is a result we've proven together with Danilo. So we've shown, so our space, in this case, our space V, it would be the space of Schwartz functions. And we say that there is a collection of Schwartz functions. Okay, so this should be. So we have a Schwartz functions C0, and then the collection of Schwartz functions AN. So they are defined on real line. And they have the property that for any Schwartz function P and any point X in the real line, we can reconstruct function P from the value of its derivative at 0, the values of the function at all square roots of integers here with both plus and minus sign, and the same information for its Fourier transform. Oh, no. Okay, so I think this should be. Fourier transform. And so this is how the interpolating functions look like. So here are the plots. And so we see that these interpolating functions here, in this case, we do have Fourier uniqueness. And so that all our functions in the interpolating basis, they also satisfy the conditions that each interpolating function, it is, for example, the first interpolating function, it has value 1 at the node 1, and it vanishes at all the other nodes. And then it's the Fourier transform of this function will vanish at all the other nodes. And so now let's consider the space of functions on our discrete sets. So here we will denote by this curly S. It will be the vector space of all rapidly decaying sequences of real numbers. So this will be our analog of our space, sorry, V of lambda and also V of lambda tilde. So these are functions which decay faster than any inverse power of a polynomial. And so this means that if we take a Schwartz function and restrict it to our sets lambda and lambda tilde, so then of course, then by the then we can get only a function which decays fast enough. And so Now let's consider the following map from the space of all Schwartz functions on real line into this direct sum of two spaces small s. And also because in our story we have this defect of finite codimension, we also need some extra information encoded in space R2. So what we do, we map our function into its, we compute its value of its derivative at 0, value of its derivative of its Fourier transform at 0, and then the values of functions at our set of function at our set lambda, and values of its Fourier transform in our set lambda. And so now what we say is we say that this space, it is an isomorphism of the space of Schwartz functions into this subspace of of this space. And so it means that for every Schwartz function, if we consider all this set of values, then there are two linear relations between them. So there are two linear relations which are satisfied by all the functions. And the first relation is given by, this is essentially, this is the summation, the Poisson summation formula for lattice Z. And the second relation, so this second relation here, it will correspond to the Poisson summation formula for the lattice Z cubed. And here R3, it is the number of representing number n as a sum of 3 squares. And so because there is a certain map between the space of functions of odd functions on the real line and space and functions in three-dimensional Euclidean space, we will have such a formula. Sometimes this is also called the Guinant formula. And so now let me speak a little bit about the idea of the proof. So yes, are there some questions? Okay, if there is no questions, then I will speak about the proof of this formula. And so what we would like to do, would like to construct the interpolation basis explicitly. And so also for us, it will be just more convenient to consider odd Schwartz functions and even Schwartz functions separately. And so here, these functions Bn, they would be the odd parts of our interpolating basis. So Bn of x, this would be they would be even functions. On the real line. And so now for a fixed number x on the real line and fixed number tau in the upper half plane. So here up h, it's the upper half plane. So the set of all complex numbers with positive imaginary part. We will consider the following generating series. So this first series is formed by the elements of the interpolating basis Bn, and second series is formed by their Fourier transform. And so now what we can do, we can apply our interpolation formula to this complex Gaussian. If we consider this Gaussian as a function of x, and we think of tau as a variable. And then if we apply interpolation formula to the Gaussian, we will obtain the following functional equation for the generating series introduced in the previous slide. And so now we know that our functions f and f tilde, they satisfy the following functional equations. So first, both functions, they are periodic with period 2. So here, here I'm using the slash notation, which is widely used in the theory of modular forms. So let me maybe rewrite this in other ways. So this means that f of tau plus 2 minus f of tau equals, so this is just equivalent to the following. So that f is periodic with period 2, f tilde is also periodic with period 2. And the last formula, it means exactly what is written here. It means that f of tau plus so now our functions, we know that our functions f and f tilde, they satisfy the following functional equations. Okay, so here, sorry, right, so this should be e to the pi x squared tau. So here I omitted the variable tau, so but variable tau is still secretly present here. And so now we have to solve the following functional equation. And fortunately, from the theory of modular forms, we know how to solve such equations. And so here again, it will be easier for us to use the symmetrization. So we define a new function f plus or minus 1, which will be either a sum of f and f tilde or a difference of f and f tilde. And then we would have this b plus of n. This would be and so now for each of this plus and minus, f plus and f minus, we also have a functional equation. And again, these functions, they are both two periodic, and they have also nice transformation property with respect to this element S, which is an involution of the upper half plane. And so the SL to Z acts on the upper half plane and by linear fractional transformation, and S acts by sending a point tau to the point minus 1 divided by tau. And so now the idea of the proof is to construct the solution of a functional equation of this kind as an appropriate contour integral. And so we will construct, for example, our function f plus as a contour integral of this type. So it will be integration by a contour which goes from -1 to 1 in the upper half plane. Or integral, then it will look like this. So here we would have our upper half plane. And so this would be our contour. And so of course, and so here we choose function k. It has to be a meromorphic kernel, and so this kernel, it is it has the following properties. So it behaves like a modular form of weight 1/2 with respect to variable tau. It behaves as modular form of complementary weight 2 minus 1/2 with respect to variable z. So this function it has. So it has weight 2 minus 1/2 with respect to z. And so we can write it explicitly in this form. And then what is also important property is that k plus it has only simple poles. And all poles of k plus are at points. Yes? Yes, want to ask something? So if the matrix ABCD, it has to be in this group gamma theta. Which is a congruent subgroup of I think of certain congruent subgroup of level 2. So the one which somehow plays an important role in the transformation rules for theta function. And also what is important is that the residues of all these poles is constant. For example, it's, I'm not sure with this thermalization, but for example, it's 1. And so that also important is that the residue at z equals to this. This has to be 1. Maybe let's do it like just some constant. And so after we construct a function like this, now of course this integral, it will actually depend on our choice of the contour. So we can, and if we choose one particular contour, then if we extend this integral, want to compute this integral for all values of tau, then what we will get a certain function which will be piecewise holomorphic. And so we have to choose our favorite piece of this function, for example, part which is, for example, in this strip around infinity. And then from this part, we would have to continue our function holomorphically through all the discontinuities, which will be the gamma theta translates of our chosen contour. And so this way we will solve this functional equation for the function f plus and also for the function f minus. Only for the function f minus, we would have to choose a different kernel here. And so now what we have to do, so now we have to construct analytic continuation of f to the whole upper half plane. And we also need to prove that if we look at the Fourier coefficients of f with respect to variable tau, and so then as the functions of x, so then here we are taking all these derivatives with respect to x. And then as a function of tau, all these functions, they should have a moderate growth at the upper half plane. And if this is satisfied, then we indeed get our interpolating formula. And also this way we can get the explicit formula. So here we would have that here. So as written before, so we have chosen only one sign here, either plus or minus, mainly for simplicity. And so now what we can do, we can take our the corresponding kernel K, and now take its Fourier expansion with respect to the variable tau. And so here we will get the Fourier coefficients, we will get functions of variable z. And these functions of variable z, they will be weakly holomorphic modular forms for the group gamma theta. They will have weight 3/2, and also certain vanishing conditions at infinity and at the cusps plus and minus 1. And so our interpolating basis, it can be computed as contour integrals of these functions Gn. Also over this contour going from -1 to 1 in the upper half plane. And so the
Maryna?
Yes?
Just to, for the sake of asking the question at this point, the function k plus, I know in these proofs there's a lot of magic. There's a lot of magic going on at various points that it's hard to motivate. But can you say something about the function k plus and how one is led to consider it, the kernel?
Yes. So this function k, I think it's a quite standard in the theory of modular forms. So idea is that we want to prove. Okay, so this we want to solve this kind of functional equation. And so the idea is that because our this function, this sometimes also called I think the reproducing kernel or Kirillov kernel. So it here in all our this functional equation is related to the action of this group of group gamma. Okay, so maybe I didn't write it down. So this group gamma theta. It is the group which is generated by S and T squared, or at least somehow it's a subgroup of SL to Z, and it acts discretely on the upper half plane. And so now we know somehow, we know that our function capital F is not modular with respect to this group. However, we know what is the defect of modularity. And so because this kernel, because the kernel K, it has poles at these points. So the points where Z is gamma theta equivalent to tau. We will know that as we are integrating our kernel over this function. Then because of this condition, when we are going to, so to say, through the singularities, we will have, so to say, this certain jumps during the translates of our contour. And these jumps, they will exactly correspond to these conditions here. So somehow this is how the contour and the kernel are especially set up, so that this discontinuities which come from integrating through the pole, they will exactly coincide with what comes out from the functional equation.
Great, thank you.
And and this is this particular shape of this kernel. So here all the functions here, so they are modular functions for gamma theta. So here this is a Haupt module. So this is a function which maps the fundamental domain of gamma theta into a projective line. And yeah, so and lambda, it's a modular invariant. It's a function which is a Haupt module for the group gamma 2. It does the same for the group gamma 2, which is a, so gamma theta, it's a subgroup of, sorry. Gamma 2 is a subgroup of gamma theta. Yeah. Gamma 2 is smaller, so gamma 2 sits in gamma theta, and they all sit in SL2Z. Okay, so and maybe so one thing. Okay, so I got a bit. And so, okay, so maybe I will just jump over here. So maybe one thing I would like to tell is that also we had the theorem and analog of this formula. So this was a theorem together with Henry Kohn, Abhinav Kumar, Stephen Miller, and Danila Radchenko. So what we have proven, so it was so we proven a second order interpolation formula from this set. So here our set lambda, it was the set of square roots of all even integers and lambda tilde, it was actually the same set. And so it means that here what for kind of information we needed was the value of function at square roots of 2n, the value of its derivative at the same point, value of its and same information for its Fourier transform. And so the only difference was that all this worked not in dimension 1, but so for our purposes, we did it in dimensions. So we did this for so radial functions, so rotation invariant functions in dimensions 8 and dimensions 24. So as these are radial functions, essentially this means that, of course, that they are essentially one-dimensional. But what differs in this case is that Fourier transform now has to be replaced by, for example, by Hankel transform. Okay, so maybe this, sorry. And so maybe the last topic I would like to talk about is the relation of Fourier interpolation and Fourier uniqueness pairs to crystalline measures. And so we say that the crystalline measure on RD, it's a tempered distribution such that both distribution mu, such that both mu and its Fourier transform are charges with locally finite support. And so what this means that our distribution mu, it can be written as a sum of delta functions with certain coefficients. And then its Fourier transform, it also will be a sum of delta functions with another coefficients. And here's the most famous example of crystalline measure is a Dirac comb. So if we take lattice Z and put a delta function into each point of lattice Z, then we know that it's a Fourier transform of Dirac comb. It will be Dirac comb again. So it will satisfy this condition. And so somehow it's an interesting question to construct such measures, but also to classify them in some way. And this seems to be an extremely difficult problem, probably an impossible one. And so there is one result by Lev and Alevsky from 2013. And they say that if mu is a crystalline measure and its support and the support of its Fourier transform are both uniformly discrete, and it means that the distance between points in both x and y is bounded from below, then mu has to be a generalized Dirac comb. So then this is the only possibility. And so generalized Dirac comb, it means that it's a Dirac comb, it's a shift of Dirac comb or Fourier transform of a shift of Dirac comb. So Dirac comb multiplied by a harmonic wave. So the only thing, and then of course we can take linear combinations of finite number of structures like this. And so we know that if x and mu are uniformly discrete, then the only way to obtain this is as a finite combination of this Dirac combs, also where the more like up to scaling, the scaling has to be commensurable so that this uniform discreteness is still satisfied. And so there are also interesting examples of exotic crystalline measures. So exotic crystalline measures are the measures which are not generalized Dirac combs. And so here there are some constructions, for example, already classical by Mayer and Guinand, and they come also from various summation formulas or from modular forms. And there is a quite recent paper by Kurasov and Czarnak where they construct crystalline measures from stable polynomials. And also it's interesting to construct these crystalline measures with extra properties. For example, in this paper of Kurasov and Czarnak, they construct exotic crystalline measures which are positive, so that the measure mu is positive. And so that now the interpolation formulas, which I spoke about before, it also gives us a family of exotic crystalline measures. And of course, if measures are exotic, it means that it cannot satisfy the conditions of the theorem of Lev and Alevsky. And so this like uniformly discrete condition cannot be satisfied. And so here, what is nice about our family of crystalline measures is that we have one point here, x, so we have measure mu, which is indexed by this point x, and x is any point at the real line. So we are putting our delta functions into the square root of n. And here the coefficients we take, they are the values of interpolating basis at this point x. And we are putting our free agent, this one more delta function with coefficient 1 at the point x. And so then this one delta function can be moving along the real lines, and all other delta functions, they will stay where they are. However, their weight will be changing. And so here, if you allow, I have a small animation of this. So can you see or not?
Yes, we can. It's kind of small, but
okay.
But it gives the idea.
Yeah. Okay, so I think now it's a bit bigger. Yeah, so here, like one window here, it's what happens, so to say, on the direct side, and this white line, like blue dots and white line, it's a direct space, and red line or gray dots and red lines, this is the Fourier side. So this is how it looks like. And so when at the end, when this red dot, which is our free electron, when it comes to 0, you see that the whole picture freezes as the Dirac comb.